Hello, everybody. How are you guys doing? I would like to thank you for coming to our consultation hour. We had a very good discussion. It's better to have the consultation hour so that by the time you are working on your module and if you have question, you can directly ask me with all your concerns so that we can directly address everything every confusion that we have regarding your topic before you submit your module by the end of the week. So thank you very much for coming to our consultation hour once again. Okay, so welcome to week 3 of our semester. So let me share with you my screen. We will be discussing another topic this morning for your module 3. All right. So module 3 talks about work and energy. So I will be discussing to you what work is all about scientifically and how do we compute for the quantity of work that is done. All right, so we already learned what work is, or we already know what this word is all about. Okay, so when we say work, it refers to um what do you do as your job, etc., etc. And if you are working on something, that is also work. Well, scientifically, are we doing work? Okay, so for this module you are going to learn a measurable definition of work as the product of force and distance. Okay, because sometimes we say that we are not doing work although we are working. So how is that? Okay, so after completing this module, you should be able to describe work in terms of force and displacement and as a scalar product. We already discussed how to compute for scalar product of vector quantities in module 1. Solve problems involving the concept of work and distinguish between the resultant work and the work of a single force. Okay, so in, aside from having resultant forces as what we had solved during module 1, we also do have resultant work. Okay, so let me give you scenarios. Okay, say for example, I am just here sitting in front of you talking with you. Of course, I am doing work literally. Okay, I am doing my part as your teacher to teach you our subject because that is my job. That is my work. Okay. However, scientifically, if I am only sitting here talking with you, I am not doing work. Why is that so? Okay. Now, there are factors that you should be considering that we can tell that you are working or not scientifically or in physics. Okay, so there are three things that are necessary for the performance of work. First, there must be an applied force. Second, there must be a displacement. Okay, so during our consultation hour, we already discussed the difference between distance and displacement. When we say distance, it is the change in position from point 1 to point 2. All right. Well, when we say displacement, it is the change in position from point 1 to point 2, and we have now our direction. So distance is only a scalar quantity while the displacement is a vector quantity. Okay? And aside from the force and displacement, the force must also have a component along the displacement. So you have to take note, a force is doing work if it is along the displacement. Okay, so let us go back to our scenario. I am here sitting in front of you teaching you. Okay, so I am doing work, I am doing my job. However, I am not moving, I am only sitting. That means there is no displacement. So, scientifically, I am not doing work because there is no displacement. Is that understood? All right, so there will be other examples for you on your module. whether you are doing work or not doing work, because there are three things that must be considered. Of course, the applied force, the displacement, as well as the force must have the component along the displacement. The force must be at the direction of the displacement, either opposite directions, as long as it is there in the direction of the force. So, right. So, here we have our scenario. We have a man holding a pot of plant and he is walking in this direction. Okay, there are two forces acting on the pot. The applied force, that is the force of the man while he is holding in that direction. Okay, while the pot also have the weight, okay, that is the gravitational force that the earth exerts on the pot, because we already also discussed during free fall what is gravitation. Okay, it is the pull towards the earth's core, so weight is the gravitational force. Okay, now since the displacement of the man is going in this direction, the applied force F does work. Okay, now this time the weight does not do work. Why is that so? Because the displacement of the pot is only along the x-axis. Okay, and there is no displacement along the y-axis. That is the reason why weight is not doing work, but it is only the applied force that is doing work. Is that understood? Okay. So if you have questions regarding that, if you have confusions, you can email me directly and I will get back to you as soon as I can. Okay, so what is our definition of work? Work is a scalar quantity equal to the product of the displacement and the component of the force in the direction of the displacement. So take note the three things that must be considered: the applied force, the displacement, and the applied force must have its component along the displacement. Okay? So work is just equal to force times the displacement. Okay? Now, let's have our example. We have our block. We are pulling our block in this direction. So we have our applied force F. Now the block moved with a displacement X. So say for example, the applied force is 40 newtons and the displacement is 4 meters. So just simply multiply the two. 40 times 4, you have 160 Newton meter. And Newton meter is equal to joule, and Joule, that is taken from the surname of a scientist, James Prescott Joule, who discovered the interchangeability of energy and works, specifically the thermal energy. Okay, so work is equal to 160 joules for this. Okay, so take note, work and energy, they're interchangeable. Later on, we will be discussing that. So stay tuned. Okay, so here we can also do negative work. Okay, how do we do that negative work? We have that if our displacement is opposite to the force, to the direction of the force that we are applying. Okay, so say for example, the same example, we are pulling our block in this direction. Okay. However, there is the frictional force. The frictional force always acts opposite to the direction of motion. So our frictional force, small letter f, is going in the opposite direction to our displacement, which is this way. Okay. So here, our frictional force is negative 10 newtons. Okay, that is our given. And our displacement is 4 meters. Okay, so our work will just be, just multiply the force and the displacement, negative 40 joules. Why is this negative 10 again? Because the frictional force, small letter f, is in opposite direction of our motion or our displacement. All right. Okay. So in our system, we can compute for the resultant work or the net work. Okay. Previously, during forces, we already solve for resultant vectors or resultant forces, and this time we also have resultant work. Okay, so from our block again, we're pulling it. Our applied force is capital letter F, and our frictional force acts opposite to that. We have a displacement X going to the direction of our applied force. Okay, so we have the work done by our applied force, capital F. We also have the work done by our frictional force, small letter f. So just multiply again, force times displacement, force times displacement for our applied force, force times displacement for our frictional force. Okay, so don't forget, take note of the negative sign because it acts opposite. So the work done is 120 joules for that one. And we can also have the resultant force, okay, multiplied by the direction, we just arrived to the same answer. Okay, so just have it in your way on how you're going to compute, whether you are going to get the resultant force first and then multiply by the displacement, or force times displacement and force times displacement and so on. But I'd rather this is simpler for you to do. Okay, now that is work for forces that are acting directly along the direction or along the displacement. Okay. Now, what if our force is acting at a certain angle with our displacement? Say, for example, we have our block and we are pulling it upward at 60-degree angle from the horizontal. Okay. This time, never forget again your Sohatoa. Okay. However, for work, we have our displacement along x. So it is cosine that we are going to use here. Okay. The x component of our force is adjacent to our angle. That's why we're using cosine. We also discussed this in our consultation hours. So I hope you don't have confusions on sine and cosine anymore, on the use of sine and cosine anymore. Okay, so work is equal to the force that you applied, the pull, 17 newtons at an angle 60 degrees, so cosine 60 degrees times the displacement, which is 12 meters. So you get your answer for that one. Okay, now how are we going to calculate for work? First is to draw a sketch and establish what is given. Second, always draw your free body diagram. I had always told you about this during our vectors for the forces that you must draw your free body diagrams. How many, so you can know how many forces are acting on your object and what will be the directions of those forces acting on your object. Okay, so find the work of a single force from formula and then get the resultant force. Now let's have our example. Okay, so let me share with you my screen here. So we can answer this example. Oh, by the way, take a screenshot for this one so that when I show, you can take a look at the screenshot. Okay, so I'll stop sharing from here. All right, so we now have our problem. Where do I go? Delete. By the way, I am also posting the PDF files of the notes that I am giving you. So everything is there provided for you. So kindly do your part in studying. The recording is there, the lecture notes are there, the slides are there, the modules are there, everything. So your part is to start working on your module before our consultation period or consultation hour each week so that by the end of the week, by Sunday, you are very confident in submitting your correct answers for your modules. Okay, so we have a 40 Newton force pulling a 4 kilogram block, a horizontal distance of 8 meters. The rope makes an angle of 35 degrees with the floor, and mu k is zero point 0.2. Mu k is the coefficient of kinetic friction. Now you are asked for the work done by each force acting on the block. Okay, so we have our block, okay, and it is also drawn there on your on in the example. It is also in the slide. So I will just be drawing again here so that you will know what techniques do we have in this. Okay, so the block is being pulled with a force P. Sorry, R ako masuwat. Okay, with a force P. And that force is equal to 40 newtons. And the force is acting at an angle which is 35 degrees. Okay, so we have a 35-degree angle for that one. Okay, now the block moves, okay, from there. I will just use not the broken lines. Okay, the block moves from there to here at a distance of 8 meters. Okay, because you are pulling the block. Okay, now the rope, um, the block is 4 kilograms. So you are given the mass of the block, therefore you have the weight. And weight is equal to mass times the acceleration due to gravity. Never forget that. We already had that. The mass of the block is given, which is 4 kilograms. And of course, our acceleration due to gravity from module 2, 9.8 meter per second squared. Our weight would be, get your calculators, guys. I want you all to be um, proactive in our course. So we have 39.2 newtons to be our weight. Now, since we have our weight, we also have our normal force acting on the block. I will have it as capital letter N. And our normal force, of course, we can compute for the normal force later because we have our force P affecting that. Okay? We cannot equate the normal force with the weight. Okay, because we have our force P. We have the y component of our force P. Okay, and of course, we are given the coefficient of friction, so it has a frictional force. And we have it as small letter f. And we are going also to compute for the frictional force. Okay, so in here, we can compute for the frictional force from the x component of our force P, our applied force P. Okay, so let us draw our free body diagram. Okay, our free body diagram, of course, we have our x and y axis. Our object is here at the vertex. Okay, so we have our force P acting in this direction. We have our weight. I will just do like that. And we have our normal force. And we also have our frictional force. So how many forces are acting on our block? There are 4 forces. The applied force P, the normal force, the frictional force, as well as the weight. Okay, so there are 4 forces. Now, our applied force P, we can separate this into X and Y components. Okay, and our angle is 35 degrees. So with that, we can get the summation of forces along X to be equal to 0, and the forces that are along X are Px, which is positive, going to the right, and we also have minus the frictional force, which is going to the left. Okay, so take note again the vectors. positive x-axis, negative x-axis. So our P sub x is equal to F. Okay, now, are we given, this time, are we given the what do you call this? The frictional force. You are not given the frictional force. You are only given the mu k. Okay, so we can get for px. Okay, so this time our px or x component along I wait, the x component of our force P is equal to P cosine 35 degrees. Okay, so why is this cosine again? Because Px is adjacent to our given angle, which is 35 degrees. Okay, so Px is equal to P. What was our given P? Our given P is 40 newtons times cosine 35. Again, get your calculators, guys. Please be proactive with this course so that we will not have our problem by the end of the semester. Okay, so kindly do your part. So we have 32.7668 newtons. Okay, by the way, do not round off your answer as what I had told you during your discussion or during the consultation hour. Only round off at the last part of your solution. Okay, so since we have our Px, that is equal to our frictional force from our first law or first condition of equilibrium, summation of forces along the x-axis is equal to 0. Okay, now since we have our frictional force, we have our formula for friction to be equal to mu k times the normal force. Our frictional force is 32.76608177 newtons, and our mu k is given, which is zero point 0.2. We can then get the normal force. Okay, so please do not be confused with this n, or maybe I will just change n. I will just change because you might be confused with that with newtons. Okay, I will change n. Sorry, I will change n. I will replace it with oh. Okay, I will replace n with small letter n. All right? Okay. So we have our small letter n, our small letter n, and small letter n. Okay, so our normal force, again, the small letter n is normal force divided by 0.2. We have 163.83 and so on. Newtons, capital letter N. Okay, again, guys, small letter n is normal force, capital letter N is Newton. Okay, now moving on. We have now our forces, frictional force, normal force, and the weight, as well as the, oh no, not yet, guys. Oh yeah, we have our forces, the pull. We have also our along the x, px. Yes, correct. We have px. We have frictional force. We have the weight, and we also have the normal force. Okay, this time we can now compute for the work. Okay, now computing for work, work is just equal to force times the displacement. Okay, now force and of course displacement, these are vector quantities. Okay, work again is scalar quantity. Okay, work is equal to force. Let us get the work done by our force P first. Okay, and force P, we must use the x component of our force P. Why is that so again? Because the work must be at the displacement, along the displacement. Okay, so we have our px. What was our px? Px 32.77 766081 32.766. Wait, guys. 08177. Oh, 7660817708177 newtons times our displacement, which is 8 meters. Okay, so our work done by force px is equal to 32.76608177 times 8. So we have 262.13 joules. Okay, Newton meter, that is equal to joule. That is the work done by our force P. Now let us get the work done by our normal force because we are asked for that. So normal force times X. The normal force that we got was 163.83. I had 163.83. I had rounded that off, by the way. So ako sa ibalik ko ha. 78177 divided by 0.2. So 163.8304089 newtons times 8 meters. Okay, multiplied by 8. Work done by the normal force is 1310.64 joules. Okay, now work done by the frictional force. The work done, wait, no way. Okay, there is no work done by normal force. Sorry. Okay, why is there no work done by the normal force? Because our displacement is only along the x-axis. Sorry guys, work done by the normal force is 0. Okay, why? That's what I told you earlier. Okay, the work must be, or the force rather, must be having the component along the displacement. So our normal force is going up, but our displacement is along the x-axis, horizontal. So work done along the normal force is 0. And work done by the weight is also 0. Now we have work done by frictional force. Our force of friction is 32 point, the same with px. Am I doing the right thing? Huh? Wait sa guys. Naglibog ko. 40 cosine 35. Wait sa guys ha. I will not be re-recording this. 40 cosine 35. Cosine 35 times 40 times 8. Okay, 262 joules. Work done by the normal force is 0. Work done by the weight is 0. And for the friction, okay. Diri ko nasayop sa frictional force. Friction. I have to get the normal force first in order to get the friction. But along X, it is just the same. Normal minus weight. Normal force minus weight. Oh, I see. Okay. Since there is the y component of our P, we cannot use this directly. But we should have the y component. So this one is not correct. Sorry guys. Our frictional force is not equal to px. Okay, px is correct already, huh? Okay, here we should have, for our FBD guys, we should have the summation of forces along y is equal to 0, so we can get the normal force. Okay, and as what I had told you earlier, the normal force is not equal to the weight because there is the y component of the applied force. So our normal force minus weight plus the y component of our applied force is equal to 0. All right. So normal force minus the weight, we already saw for the weight earlier, 39.2 newtons, plus our P sub y again, for this one is sine. Okay, earlier our P sub x is cosine, so this time we have our sine. So P sub y is equal to P sine. Why is it sine? Because P sub y, if we are going to transfer it here, P sub y will be opposite to our angle. All right. So here, our P is 40 newtons times sine 35 degrees. P sub y is equal to, again, get your calculators, please. Sine 35 times 40 is equal to 22.94. 35,745 newtons. All right, so plug in P sub y here, 22.94 newtons. Oh, ano man ka. Okay, so 94 na siya guys. Dili na ko kasulat guys. Is equal to 0. So we can get N for that one. So 22.94 minus 39.2 transpose to the other sides. You know your algebra already. So we have 16.26 newtons. I will just round off here, but in your calculator, do not round off, okay? So we have your normal force to be 16.26 newtons. Okay, back here. Normal force is 0. Weight of the frictional force. Friction is equal to mu k times normal force. Mu k is given 0.2 normal force. What was our normal force? 16.26 newtons. 16.26 newtons. Gapas ko guys ha kay mataas ang time, mas dugay i-upload ang video. So 3.25 newtons. So 3.25 newtons. Sorry guys. Wait. Okay, that is the friction. 3.25 newtons times 8 meters. And again, friction is opposite, so this should be negative here. So 3.25 times 8. So negative, atong klarohon be? okay, is equal to negative 26.01 newtons. Okay, so these are the work done. The work done by the force 262 joules. Sorry again. That is joules. Okay, so we have our work done by the applied force. Okay, work done by the applied force 262. Work done by the normal force 0, y0. Normal force is along the y-axis and our displacement is along the x, as well as the work done by the weight is 0. Okay, and work done by the frictional force is negative 26.01 joules. And if we are asked for the network will just be equal to the sum of all the forces. And we have 262 minus 26. Our net force, oh, our net force will just be equal to 236 joules. Okay, if we are asked for the net force, but we are asked for the forces that are I will charge first that are or we are only asked for the work done by each force rather. Okay, so let us now proceed to the next part. I will be sharing to you my screen again. Purag taas-taas na gyud niyang ato ang recording. Dugay na pud ko og upload ani. All right. So my screen is there again. Let me check. Nawala na pod. Okay, so let us now proceed to Hooke's law. Okay, so Hooke's law, these are for springs. Okay, so when a spring is stretched, there is a restoring force that is proportional to the displacement. So F is equal to negative Kx. Okay, the spring constant K is just a property of a spring given by the change of the force over the change of the displacement. Okay, so you are pulling the spring here, you have your mass, and the restoring force is opposite. That's why we have the negative sign there. The negative sign means that the restoring force due to the spring is in the opposite direction to the force which caused the displacement. Okay, so the work done in stretching a spring is equal to 1 half kx squared. Okay, and we already said work is interchangeable with energy. So the energy for the spring, which is elastic potential energy, we will be talking about the different types of energies later on, will just be equal to 1 half kx squared. Okay, so for compression, the outside force does the positive work and the restoring force does negative work. And for stretching, the outside force does positive work and the restoring force does negative work. Okay, so let us have our example for that. We have a lot of examples this morning. Okay, so kindly take a screenshot of our first example so that when we solve, you can take a glance at the problem. Okay, so you have a spring and it stretches 10 centimeters when a force of 20 newtons applied on it. You are asked for the amount of energy stored in the spring, that is the elastic potential energy, when it is compressed 5 centimeters and when if it is stretched 10 centimeters. Okay, so I will be sharing my screen again with you. Alright. Do you have my screen there already? Is it there? Yeah, it's there. Okay, so you have your spring and you have your applied force, which is 20 newtons, and it stretches. So you have your x to be 10 centimeters. Okay, so This time, take note, you have to be consistent with your units. Okay, since we are having newtons, we must have meters. Okay, so you are asked for the energy stored. So you are asked for the elastic potential energy when it is compressed 5 centimeters and when it is stretched 10 centimeters. Okay, so here you must use Hooke's law. Hooke's law is again spring force or restoring force of the spring is equal to negative kx. Okay, where k is the spring constant and x is the displacement. You are given the spring force, which is 20 newtons. We can compute for the spring constant. And you are given 10 centimeters. Get your calculators again. 10 divided by 100, you have 0.1 meter. And our spring constant would be inverse. Okay, here would be 200 Newton per meter. That is our spring constant. And we will use our spring constant in order to get for the work. Because we are asked for the energy, work is equal to the elastic potential energy, and that is equal to 1 half kx squared. That is our given formula. Okay, so that would be equal to 1 half. You use this one, 200 Newton per meter, x squared first, compress 5 centimeters. Okay, so we have to have 5 in meter. Okay, 5 divided by 100. Solar ang ako ang kuan. Akong calculator. Dayon walay sun karon. It's 10 a.m. yet it feels like 6 p.m. outside. Okay, walay sun. Okay, so meter squared. All right, then our elastic potential energy is 0.25 meter cancels out and the other meter cancels out. What remains is Newton's times meter, or that is joules. Okay, so that is our answer for letter A. Now for letter B, if it is stretched 10 centimeters. Okay, so our elastic potential energy again, 1 half. K is already given to, K has been calculated. And point 1, 10 centimeters, stretching 10 centimeters. So 0.1 meters squared. Do not forget it is being squared. And our EPE is, by the way, I will erase that and I will transfer that here. Okay, our elastic potential energy is 1 joules for that one. Okay, now talking about energy. No, we let's not proceed yet to energy. Let's have power first. Okay, so power is the rate that we use energy. Okay, so or it is the rate of doing work. So power is equal to work or energy per unit time. So we have our formula for work to be joule and our time, it must be in seconds. So we have joule per second and joule per second is equal to watt. Okay, so where does watt came from? W-A-T-T. Watt comes from the scientist James Watt. Okay, and 1 horsepower is equal to 746 watts. So this is just very simple calculations for power. Okay, so say for example, we have a 5 kilogram cart pushed by 30 Newton force at a distance of 10 meter in 5 seconds. Okay, so just multiply force times distance, that is work, divided by the time. Okay, so power is just the time rate of change of work. So force times the displacement divided by time, you have your power, which will be equal to 60 watts. Okay, so joule per second is watt. So that's just all about power. Now let us now have energy. Okay, there are types of mechanical energy. Okay, potential and kinetic. And for potential energy, we have the gravitational potential energy and the elastic potential energy, as well as the chemical potential energy. Okay, so when we say gravitational, potential energy, okay, it is the energy that is stored in an object due to its position. Okay, so our formula for that, PE is equal to mgh, where m is mass, g is the acceleration due to gravity, and h is the height. Elastic potential energy, just like the spring that we had, is the energy stored for objects that can be stretched. Okay? And chemical potential energy is the energy stored within chemical bonds. Okay? So we have chemical potential energy stored in our batteries. Okay, so now kinetic energy, as what we always say, it is the energy that is due to its motion. So the formula for kinetic energy is 1 half mv squared, where m is the mass and v is the velocity. Okay, now, say for example, no, not yet. Okay, so what is this for? This is for the conservation of energy. Okay, so let's have first examples for computations for our potential energy. So again, PE is equal to mgh. We have 50 kilogram located at 5 meters. Find its potential energy. Okay, so we have our mass, 50 kilograms. Our acceleration due to gravity, 9.8 meter per second squared, and our height is 5 meters. Okay, so what we have here, just multiply everything. 50 times 9.8 times 5 is 2,450 joules. Okay, why is that so? It is in kilogram meter squared per second squared. Okay, um kilogram meter per second squared is equal to this one. Kilogram meter per second squared is equal to newton, and this one kilogram and meter per second squared, and you still have newton. Newton times meter is equal to joules. Okay, that's why we have our PE in joules. Okay, now number two, that would be for your exercises. Okay, now for kinetic energy. For kinetic energy is equal to 1 half mv squared. So we have 1 half, m is 8 kilogram, and v is 5 meter per second, and we square that. So 5 squared times 8 divided by 2, we have our kinetic energy to be 100 joules. So, okay. So why is a joules again? We have kilogram again, times meter squared over second squared. That's what happened here. Okay, so this kilogram meter per second squared, that is again equal to newton, and we have the meter left, and newton times meter is equal to joules. That's just it. Okay, so very easy, just multiply everything. Okay, now let us have the conservation of mechanical energy. This time there will be confusions. Okay, so we always say that energy cannot be created nor destroyed. The total energy coming in the system is equal to the total energy coming out from the system. Okay, but they are just in but energy converts from one to another. Okay, they are just convert interchangeable or convert. How do you know? How do you um what do you call that? How do you define that one? Okay, so here we have our roller coaster. Okay, so at the highest point of our roller coaster, okay, of course, it possesses potential energy. All right. So, say for example, this is our datum. Okay, our datum is this. Ay, why? Um, Drawing tools. There you go. Where is the No, not that one. So, ang gani pagsulat-sulat there is a slide, guys. Nakasulat-sulat naman ka. Ah, there. Start inking. Ink tools. Okay. So, this is our datum. I will change the color. I will change the color of my pen. All right. Very good. There you go. Okay, this is our datum. Just consider it a straight line, guys. This is our datum. When we say datum, that is our reference point. Okay, so we have a great distance here of our roller coaster. Okay, so we have a great amount of h. Oh, wait, I know I am not sharing my screen. Share screen. Sorry, sorry. Okay. Okay, there you have it. Okay, do you see my screen now? Of course, you're seeing my screen. Let me check. Okay, there it is. Okay, so again, we have our datum. The datum is this, our reference line. Consider that as a straight line. And we have our height. Okay, the distance of our object, which is our roller coaster cab. And from our datum. Okay, so from our formula, PE is equal to mgh. If our h is increasing, that means that the potential energy also increases. So at this point, our PE here is maximum. Okay, why is it maximum? Because it is at the greatest height. Okay. Now, if our roller coaster cub reaches this point here, our PE will be equal to 0. Okay. Why is our PE is equal to 0? Because there is no height at all. Okay, H is equal to 0, so PE is equal to 0. All right. Now, for our object that is here at the highest point when the PE is maximum, our KE will be equal to 0. Okay, why is that so? Because all of our energy is in the PE. While here at the lowest point, our kinetic energy, our KE is now, it's very hard to do this. Okay, KE is maximum. Why is it maximum? Because our PE is 0. So all of our energy at this point is the KE. And at each point here, at each point, the total energy is the same, but PE and KE varies. So at this point, okay, as our curve is going down, PE is decreasing while KE is increasing. Okay, as the curve is going down again, PE is decreasing, approaching 0, while KE is increasing from 0 to maximum. Okay, because of the conservation of energy. Okay, so another example we have here, the same concept. PE here at the highest point, our datum is this again, is maximum while KE is 0. And as it goes down the slope, KE is increasing while PE is decreasing and approaching to 0. Okay, so let's have this as our example. We have our pendulum. Our datum is this. Okay, so we have points A, B, C, and D of our pendulum. Now at point A, we are given that KE is 0 and PE is 2.4. Okay, because here at the starting point, there is no motion. Okay, so all of the energy is potential energy and kinetic energy is 0. Now, as the pendulum reaches point B, KE it becomes 2. Now, what must be PE? PE this time will be equal to zero point 0.4 joules. Okay, why is it zero point 0.4 joules? It's because the total energy of the system is 2.4 joules. Okay. Now at point C, our pendulum is here. The PE is 0. The pendulum do not have the height. Okay. So our KE will be 2.4. Okay, by the way guys ha, the broken lines pala here is not our datum. Okay, it's not our datum, but our datum is this. The datum is this. Okay, consider this as a straight line. Now, KE at point D, again, the pendulum momentarily stops. So KE is 0 and our PE will be 2.4, the same as point A. Okay, and we have here our example, another example for you to practice. Okay, so let's have this. Number 2, our last example for this morning's discussion. We are over time. The answer choices will be maximum value, minimum value, the same value as at every point in the orbit, and none of the above. Okay, so our question. At perihelion, we have here perihelion, the gravitational potential energy of Pluto's orbit has. What will be the PE? Okay, when we are going to compare aphelion and perihelion, H is lesser here. So what would be the gravitational potential energy if H is lesser? It will be minimum value. Okay, for that one, the answer is letter B, minimum value. Okay, now at perihelion, the kinetic energy of Pluto has, since the GPE is minimum, therefore the kinetic energy is maximum. Okay, so the answer for number 3 is letter A, maximum value. And number 4, I will just do this na lang, ha? Number 4, at perihelion, the mechanical energy of Pluto's orbit has, what would be the mechanical energy? That is the total energy. So as what we have said, the total energy will be the same at every point. Okay, so the answer is letter C, the same value as at every other point in the orbit. And finally, as Pluto moves from the perihelion to the aphelion, the work done by gravity on Pluto is, Pluto moves from perihelion to aphelion, so the displacement is going in this direction. The work done by the gravity would be A0, B positive, C negative, or none of the above. Work done by the gravity, of course, it is being always pulled towards the sun. So is the displacement of that work done? Okay. The same. Is the direction of the work done the same with the displacement? It is not the same. So the answer would be 0. Okay, so that's it for this modules discussion, guys. We are over time and it's hard to upload these anymore. So if you have questions, you can directly inbox me on Canvas so that I can address your questions right away. And please do answer your modules, start working on your modules before our consultation hour each week so that during consultation hour, you can give me your questions and you can give me your concerns and everything so that we can be on the same page, and by the end of the week, that's the time you're going to submit your modules, so you will be very confident that all your answers are correct. So kindly do your part. All materials are given for you. Thank you very much for watching, and see you again for our consultation hour.